Aerospace is one of the things that helps people get high up in the sky, and to fly to any location people need or want. Aerodynamics has been around for a long time, even back in the 1700s. Even though it is old, it plays a major role in today's technology. Aerodynamics is the study and use of the flow of gas, specifically air. It is used in making aerodynamically sound aircraft. It's so important for aircraft and spacecraft that it has to be considered in the design process. Let's start with the foremostly known forces, lift and drag. Lift is the force from air molecules hitting the wings of an aircraft. This is the force that pushes the aircraft or spacecraft upwards. Lift is a need for aircraft to even get off the ground. Lift is calculated through computational fluid dynamics or through actual tests of aircraft or spacecraft. Drag is the force slowing the aircraft or spacecraft down. There are multiple types of drag that I will elaborate on in different videos. But for now, it can be a nuisance, or it can be a form of safely slowing something down. In the case of aircraft, it is mostly bad. For spacecraft, however, trying to re-enter the atmosphere is almost always bad news for spacecraft going at hypersonic and higher speeds. But what is this hypersonic? There is this thing called Mach. It is how many times the speed of sound you are going. Subsonic is the speed regime below Mach 1 or 1 times the speed of sound. Most aircraft at this speed are usually aircraft with simple rectangular wings, and gliders. It is usually safer to fly in subsonic aircraft. Then there is transonic, which is the speed regime between Mach 0.7 to Mach 1.2. This is the speed regime where most jet aircraft fly at. Here is where drag starts becoming more of an issue. When the spacecraft come in contact with the air around it, it creates a shock wave. This is where engineers have to start taking compressed air into consideration. Supersonic is one of the more rare speed regimes for aircraft. At these speeds, depending on the Mach, the shock wave achieves a more steeper angle. At these speeds, a boundary layer forms. Inside this boundary layer, air becomes viscous and more unpredictable. We only recently broke the sound barrier in 1955 by Chuck Yeager, a test pilot. Back then, they believed it was impossible to go faster than the speed of sound. When Chuck Yeager broke the sound barrier, he thought his measuring equipment was malfunctioning. Now, the only few passenger aircraft to fly in the supersonic regime was the Concorde and the Tu-144. Now we're on to the final speed regime, hypersonic/high hypersonic, which is Mach 5 and above. Speeds like these are easy to come by in a place without an atmosphere. However, Earth has an atmosphere. Hypersonic speeds are hard to come by because the air gets hot, and by that I mean really hot. Hot enough to melt steel. Thanks to this, there have been only a handful of manned aircraft spacecraft to achieve this crazy speed. 2 of these you probably know. The X-15 was a hypersonic aircraft that could go at Mach 6.5. The X-15, like those handful of hypersonic aircraft, had a dart-like shape. At hypersonic speeds, the shock wave is so close to the aircraft that the angle can reach up to 5.73 degrees from the aircraft. The Space Shuttle, all of them, re-enter the atmosphere at hypersonic speeds. When the Space Shuttle re-enters the atmosphere, it faces downwards to increase drag to slow down. But when they re-enter the atmosphere, the air predictably gets really hot. To counter this, the Space Shuttle uses Lean 900 silicothermal-resistant tiles. However, the shuttle needed 21,000 of these tiles, and each of them had to be either checked or replaced. If any of these tiles malfunctioned, could have led to the deaths of the people on the shuttle, which happened on STS-107 in 2003. We'll be looking more into the space shuttle in later videos. We looked at the basics of flight regimes and basic properties of air. This is the first episode of what's to come. This is the end of the video.